A string is wrapped around a disc of mass 2.1 kilograms starting from rest. You pull the string with a constant force 9 newtons along a nearly frictionless surface. At the instant when the center of the disc has moved a distance of 0.11 meters, your hand has moved a distance of 0.28 meters. So I've drawn a picture to show. So this is the distance 0.11 meters that the disc has moved. The disc weighs 2.1 kilograms. The hand pulls with a force of 9 newtons, and then this is the 0.28, which shows how far the hand has moved. So my questions are, A, at this instant, what is the speed of the center of mass of the disc? So right here, I have A, and our system is going to be the point particle system, where we have work is equal to the change in energy, which is equal to force times change in R of the center of mass, so change in position. And that way we have kinetic energy is equal to force times change in R, which is your distance of the center of mass. So we're going to do K2 minus K1 is equal to force times change in R of center of mass. Then we know that we have 1/2 mv(f) squared minus 1/2 mv initial squared is equal to the force times change in R, which is center mass, which this is also your work equation. Then we go to where we can go ahead and solve. We're looking for V final, so when we do that, we end up with V final is equal to the square root of 2 times the force times the change in R over the mass. And when we plug in the values, we were given, so we know 2, we were given the force of 9, we know that our distance is 0.11 meters, and our mass is 2.1. So when we do that, we get 0.0971 meters per second. And then for question B, it says, at this instant, how much rotational kinetic energy does the disc have relative to its center of mass? So for B, we're going to use the real system, where work is equal to the change in energy of the hand. So work is equal to force times change in R, which is once again the distance, is equal to the change in kinetic translational plus the change in kinetic rotational. So work is equal to change in kinetic plus change in rotational, final minus initial. We know our initial is going to be 0 because it wasn't moving in the beginning. That way, we're solving for rotational, so K rotational is the kinetic energy of rotational is gonna be equal to the work, which is force times change in R, minus the change in kinetic energy of our translational. So that way we can do K rotational is equal to 9 newtons, which is our force, times 0.28 minus 0.11, because that's the distance, and we end up with 1.53 joules. So that is how much kinetic energy the disc did. And then for question C, it says, at this instant, the angular speed of the disc is 7.5 radians per second. What is the moment of inertia of the disc? So right here, we know what we were given the equation K rotational is equal to 1/2 I, which is inertia, times omega squared. So we can rearrange this equation to where we're looking for inertia. So I divided it by omega squared, and then I added the 1/2, which ends up being multiplying by 2. So I is equal to 2 times the kinetic energy of rotational divided by omega squared. And they give us omega in the initial equation by saying, in the question by saying 7.5 radians per second. So we know that I is equal to 2, because that's from bringing this 2 to this side, times 1.53 joules, which is what we found in part B right here, that kinetic energy. And then we divide that by our omega squared, and we end up with 5.44 times 10 to the negative 2 kilograms times meters per second squared for the moment of inertia of the disc.